Okay.
Okay, welcome to the weekly seminar of the Nuclear Engineering Department. It is my pleasure to introduce today's speaker, Dr. Sebastian Schunert, who earned his PhD in 2014 from NC State, Nuclear Engineering, of course. After that, he went to work at INL. He's currently at the position of a staff scientist. His expertise is focused on radiation transport methods for multiphysics applications, and of course, as the title tells you, that he puts his products in the most multiphysics environment product. His research involves multiple things, and we're going to hear about some of them today, including next generation modeling and simulation tools applied to advanced reactors, including molten salt, pebble beds, and thermal propulsion systems. I add also that Sebastian is a joint assistant professor in our department from INL, so he is a participant in many of the activities of the department. Thank you, Sebastian, for doing this, and please take it from here.
Yeah, thank you, Yusri, and it's really an honor to give that presentation. I've sat in that room many times, about a decade ago. Yeah, the talk is about modeling advanced reactors with MOOS. But before I get into that, I want to give credits. This is not work that I've done alone. There are many people that have worked on portions of this research, and the names are here. I color-coded them by INL, ANL, Texas A&M, and TerraPower. Lots of funding agencies involved as well. I won't read them out to you, but this is not the work of a single person, that's the work of a team. First, I want to introduce Idaho National Laboratory a little bit. So Idaho National Laboratory fits into this Department of Energy laboratories that are all across the country. And we are in the blue one here, the star, up in eastern Idaho, Idaho Falls. And we are the primary nuclear engineering lab in the country with a lot of great facilities out here. INL is, I think, at the forefront to address the world's most challenging problems. And that runs the gamut from nuclear science and technology on the very left. That's where I am. We have the advanced test reactor here. We have the MFC facility, a big hot cell. And then we have probably lesser known the ES&T division and a big part of national homeland security. So we are focused on nuclear energy, but there are also other branches of research that we do. Eastern Idaho is, of course, a great place to live. And if you like skiing, for example, upper left-hand side, that's a view of the Tetons from the Idaho side. So that's Tagi, and all kinds of other outdoor activities that you can do here. So if you're into outdoor activities, Idaho Falls is really a great place to be. Moving on to the team I'm working in. We call that the Reactor Multiphysics team. And it really is concerned with two things. The first thing is the development of applications for multiphysics analysis of advanced reactors. And the two that we develop the most are Griffin, which is an electronics application. I'll talk about that a bit more. And Pronghorn, which is a core smash TH application. And these are mostly developed within the NEAMS program. But we also do a lot of analysis, and that is with companies. We partner with companies through gain vouchers and the Advanced Reactor Demonstration Project. And we also work with the NRC. So we advise them on tools for advanced reactors. So we have projects in the area of algorithm development, implementation, and reactor analysis, and a large number of reactors we work on. Pebble bed reactors, FHRs, MSRs, nuclear thermal propulsion systems, and more. The department I work in is the Reactor Physics Method and Analysis Department. And that's really think of it as like my column orientation, where the team is my row orientation. The goal here of this department is develop and apply modern tools and techniques to fully characterize current and advanced nuclear reactor design and systems in support of testing, licensing, and deployment wherever energy is needed. That goes to integrated energy systems, hydrogen, renewables integrated with nuclear energy. We are instrumental in the fission battery initiative, so modeling of autonomous fission batteries. We are involved in technology maturation with Marvel, and then also, and that's where I'm mostly active, in the next generation advanced reactor codes, and you'll hear a lot more in the following slides. We are hiring, so I would like to give the link to the department so it can be shared among the graduating students. So we're looking for a nuclear engineer with multiphysics background and one with neutronics background. So we are growing. So let's get right into the technical area. I want to first motivate the advantages of MOOS. So MOOS is a multiphysics object-oriented simulation environment. And you probably heard about it by this time. It is really a great application to develop your advanced reactor code in, because it gives you a lot of flexibility and a lot of capabilities that you don't have to you don't have to reinvent the wheel. It is very flexible. So multi-D, 1D, 2D, 3D, RZ, all relies on the same code base. It allows you to what we call a multi-scale calculation using a multi-app. So multi-app is basically one app owning other applications, and you can actually just do whatever you want with these applications. So you can run Picard iterations, you can do multi-scale analysis, you can run them on smaller time steps, so that would be subcycling. And most importantly, it's extendable. So you can add your own physics to it. It's mainly open source. And then the applications you can keep for yourself, and they would basically just depend on those. It's also, it's a tunable fidelity framework. So we do high fidelity work, but we go all the way down to 1D and 0D lump models. So you see that when I talk about Griffin, quite a bit more so on neutronics code. And finally, MOOS is scalable. If you want to run a 2D or RZ model, you run it locally, and your models will execute in minutes. If you want to run 3D, you execute as an HPC, and you can do that. It's the parallelism is all taken care of for you. So these are really the advantages of MOOS and why I think it's been successful in the past. We refer to these, so MOOS has a theme of applications, and these applications, they perform different tasks, but they're all named after animals. So what I refer to them is the moose herd. So you would have, so for example, Bison would be a code that does fuel performance. Griffin, it does radiation transport. Pronghorn does engineering scale flow. So you have these applications that are built for a particular task, and you give it an animal name. That's then referred to as a herd, but they all work together. So if you want to run multiphysics simulation, you can always take them and mix and match them, and they will all work together and execute together, so you can simulate your multiphysics problem. So this is the introduction for Griffin. Griffin is our neutronics code. It is a very generalized tool for reactor physics, and it's geared towards non-light water reactor applications. So why is Griffin important within, let's say, the greater scheme of needs? If you look at reactor applications, many of the other codes would swap out. So let's look at FHRs, SFRs, and MSRs on the upper right-hand side here. So in order to simulate that, you certainly have to have a system code. Okay, and that would be SAM within the NIMS framework. But you also need neutronics. So neutronics is in that mix, and Pronghorn potentially for multi-dimensional flow. On the other hand, if you want to do microreactors, you also need Griffin, but instead of SAM, you would use Sockeye, and you would use Bison, Bison being pure performance in that case, and Sockeye doing heat pipes. So whatever reactor you do, you will need Griffin for that, because neutronics drives the whole problem. That's why Griffin is so important, and it's really of central importance within all the things we do. The difference between Griffin and other codes is really that it's multiphysics oriented. It immediately provides native coupling with smooth-based tools. So you can solve problems concurrently without having to write your own interface with it. So you can just plug in and play and solve your multiphysics problem with neutronics. And that really is based on this common investment in the Moose framework. That's what makes this possible. It's not glue code, it is really a common framework. It's flexible and extendable. So you can add your own functionality relatively easily. And it allows you to do variable fidelity. We have a diffusion solver, we have an SN radiation transport solver. So that shows you have different types of solver options depending on what you want to do, what kind of fidelity you're looking for. And finally, it is consistent with an NQA1 process, and we abide by strict software development cycles. So the software quality is high in the software framework. I want to take the time here to share some of the newest improvements within the Griffin transport solver, which I think the team is quite proud of. The SN solver in Griffin has been relatively slow on grind time. And the fiscal year 21, so this is just this last fiscal year that just passed, has seen a great improvement of the SN transport solver. And what you see here on the right-hand side is a challenge problem that we have. So that's a two-dimensional treat, I believe. It's a slice of treat. And then in the bottom, you see the run times where we compare Griffin, accelerated with coarse mesh finite difference, CMFD, with Proteus. And Proteus uses the method of characteristic option here. And you see that it's comparable in both memory and execution time. So with these, with this performance, Griffin with SN method moving forward is going to be a much more useful and a much more useful tool for analysts. The other code that we use a lot is Pronghorn. So what's Pronghorn? Pronghorn is a coarse mesh thermohydraulic core simulator for advanced reactors. So if you look at the reactors on the right-hand side, all of them have one common element. That is, they have multidimensional flows that are important. And if you have multidimensional flows that are important, Pronghorn will offer you some capabilities that are really great, I think. If you do CFD, you cannot solve transients on a laptop in a reasonable amount of time. Pronghorn is not meant to do CFD level calculations. It's a coarse mesh solver. Think Relab 5 3D with a modern interface for advanced reactors. So with more geometric flexibility and the ability to couple it. So Pronghorn is really in this hierarchy of there's a CFD hierarchy of accuracy and scale resolution versus lump models that you see on the left-hand side. It really sits in this engineering scale level where you have porous media, subchannel, coarse CFD, and that's really the area that Pronghorn works in. It is really, it builds on capability that exists within the Moose framework, and then it actually implements some of it itself. So for example, there's a subchannel solver that's developed, Pronghorn uses that. It uses Moose Navier-Stokes, so that's a module under Moose, and that physics is used within Pronghorn. It also pulls in THM, which is a library for system modeling. So think a library that Relab 7, let's say, is based on. And then finally, porous medium. So for pebble bed reactors, for example. So let's get into some examples of work we have done. And let's start with pebble bed reactors. The first example I want to give you is a safety-related transient that we have done with Pronghorn and what goes into that transient. So this transient here is a pressurized loss of forced cooling. So what happens is you run your pebble bed reactor at full power, and then your circulator ramps down. So you lose forced circulation. And the event sequence that leads to that, you see on the upper left-hand side. So 13-second linear reduction in a reactor inlet coolant mass flow, and then a reduction from 90 to 60 bar of the reactor outlet temperature. From 13 to 16 seconds, you insert control rods and you scram, and then you leave the reactor to its own devices for the next 50 hours. The particular geometry we use is the PBMR 400 benchmark. The PBMR 400 benchmark is really takes a South African PBMR design. It's a 400 megawatt design, and simplified a little bit to make it a benchmark. That's really what the PBMR 400 benchmark is. And it is the only multiphysics benchmark that, as far as I know, that we have for pebble bed reactors. What goes into this is really are these boxes on the left-hand side. So it's how we really build these models. So we build the transient, NK here is for neutron kinetics, transient plus the iodine and xenon tracking. Then we build another model, which is a TH transient model. And finally, we have 1D pebble model. So you want to know the temperature of the compacts, and you want to know the temperature of the trisols, and you need to back that out from the temperature of your coolant. So that's another problem. And these problems, the way we solve them, we build them separately, and when we connect them using the Moose multi-app system. Okay, and then we can exchange information between them using multi-app transfers. Fuel average temperatures over time are plotted on the right-hand side, and you see that Pronghorn is right there with the two other codes that are, in quotes, trustworthy, that agree with each other. That is DORT TD, and that is also Tinte, I believe, yes. The other two codes are not that, well, they disagree quite a bit, so I wouldn't trust them too much, but we are very good, we compare very well here with other codes that have solved this problem. Runtimes here about 20 minutes for the transient on a laptop computer. Another problem that we have worked on in the past, and we're still working on it actually, is pebble depletion. So if you are not familiar with it, a pebble bed core is this cylindrical vat, really, with, let's say, a few 100,000 pebbles in it. Pebble is a 6 centimeter, so like a tennis ball sphere of graphite, and it moves through the core. So they enter on the top here, and then they move through the core, and you remove them at the bottom. You measure them and see how much burnup they've seen. If they have seen too much burnup, you remove them and you replace them by a fresh pebble. If they don't, if they're still good to go back, then you recirculate them back. So the problem here really is depletion, but with slowly moving fuel. Okay, it's slightly different in MSRs where the fuel moves, but it moves much faster. But here in this case, it moves slowly through the core, and then it's potentially recirculated, but might not be recirculated. How we solved this is we used an Eulerian control volume approach. So we discretized this problem along streamlines. Well, one of the things that we know is pebbles mostly move in 1D lines. They don't cross or anything. There's no 2D component to it. It's really they move along these 1D streamlines. So you discretize the streamline and you solve the relevant equations on the streamline. Then when they hit the bottom, then you basically need to apply a boundary condition, and that boundary condition either recirculates it or not. So that's our approach here. What we have used that for is equilibrium core calculations. So if you run the core for a sufficiently long time with a constant recirculation scheme, then it will actually achieve a time-independent state at some point. And that's the equilibrium core. So that's what we've solved so far. What I want to point out on this slide here really is the concept of how this works. You have multiple streamlines, number them from k equal 1 to k. Then you solve it's really a PDE on these streamlines. You discretize them into elements. You solve a PDE on those streamlines, and then you compute the outlet condition here. Okay, and then we have this pebble handling system. That's a red piece that's outside of the core. And the pebble handling system in reality is a big pneumatic system that gets pebbles wherever they need to go. But in the code, it is really a sophisticated boundary condition. So it's a periodic boundary condition with twist. That's really the best way of thinking about it. Okay, why is this important? Why do we care so much about pebble bed reactors right now? Two things. First, one of the ARDP awards is actually X-Energy, and X-Energy wants to build a pebble bed reactor for this ARDP. In order to do that, we need codes that are NQA1 within the United States and can be accepted for licensing calculations. And these codes currently do not exist. So that's one reason why this work was kicked off. Another thing that makes this quite a timely development is that China just ramped up their HTR-PM, which is a 200 megawatt electric reactor demonstration plant built in China. So it's HTR-PM, and you'll see that in a second. We have what we call an HTR-PM reference plant, and I'll explain what that is. So that #1 reactor achieved first criticality on 12th of September of this year. And we will hopefully get a benchmark data through the Gen 4 program very soon from this. Okay, so we built this HTR-PM reference plant model, and it's if I say reference plant model, what I mean is you take publicly available information about a core. We are not the engineers of this core, so we don't know all of the specifications. So whatever we don't know, we just try to infer by engineering judgment. And then we build our model for that, and you see the model on the left-hand side. It's a 1.5 meter radius, 11 meter high, so that's the pebble height. The bed height is 11 meters, and 7 grams of initial heavy metal per pebble. Number of passes is 15 in this core. So that means before you discard a pebble, you recirculate it about 15 times. The number of streamlines is really how fine do we discretize the path of pebbles through the core, and we determined that 6 is a good choice. And then the rest, can go through that average residence time, discharge burn up, and the neutron libraries, which were created by Dragon. So what you see here, how does this model look like? It's a quite simplistic model, really. The Griffin computational mesh on the left-hand side there is a Cartesian mesh, but it's RZ, of course. The pebble bed is in gray, and then the reflector around it is red. That's the bottom, top, and side reflector. And then you have a control rod is blue, and empty control rod channel is green. And then you see overlaid the Griffin streamlines. And that's what I plot here is a particular quantity called partial power density. It's not too important what that is, but that's how the solution would roughly look like. So it's nice because we have published results for this core. And the published results come from VSOP. And these results were obtained in China. So it's VSOP, and I think there's a Chinese version for it. VSOP is a legacy tool. So it's a legacy tool originally developed in Germany decades ago, and it was then picked up and is used quite a lot in China. And we compare to these published results here. So left is VSOP, right is Griffin. So we match the eigenvalue quite well. So it's 1.00061 versus assumed 1, and we don't know that wasn't reported in VSOP. The maximum power density, we agree quite well. So it's 0.58 and versus 0.57. And you see that the power distribution also looks reasonably well approximated, or reasonably well in agreement. And the power peaking is also quite close. So we are fairly happy with this comparison, this initial, call it code-to-code comparison. And but we are working towards a full verification of this equilibrium core capability within the Advanced Reactor Technology program. That's ART, and that will use a Serpent full core equivalent model in that case. So that would be a nice comparison. So I want to switch gears here and go to molten salt reactors. Why are molten salt reactors interesting? Why is that also a timely thing to invest your money in? One of the AIDPs is the McCree project from Southern Company, and that will hopefully be built at INL. So at INL, MSRs will be a reality. And there's multiple people multiple initiatives that work on that. The National Reactor Innovation Center, the AIDP, and NSNT's Fission Battery Initiative also works on that. This McCree or molten chloride reactor experiment will give us great unique validation opportunity for our tools, and it will serve as a licensing basis for reactor transients later. So that's why molten salt reactors are very interesting for us. So what have we done? What do we use to model molten salt reactors? We use, again, the two tools that I showed you, Griffin and Pronghorn, where Griffin, we use neutron diffusion, and Pronghorn is basically the thermohydraulics. So thermohydraulics computes the velocity field and the pressure field, while Griffin computes for you the eigenvalue, delayed fractions, and the neutron flux. And then we interact, the two codes interact with each other using Picard iterations, or we can also accelerate these Picard iterations, where the power profile and fission source is sent to Pronghorn, and the temperature distribution precursor concentration is sent to Griffin. What you see on the right-hand side is the steady state temperature distribution for the molten salt fast reactor. That's, I think, from the Samofar project. It's a 3,000 megawatt thermal reactor. So it's a big machine. Okay, so that's a lot bigger than I think the US designs would be. It's a radial symmetric model at this point, and we're looking into 3D later on, but currently we are focusing on radially symmetric models. The heat exchanger and the pump that's in that, if you see it's located here, is modeled using a porous media approach. And the heat exchanger basically uses a conjugate heat transfer, H times delta T kind of terms. We have done steady state here, and we have done a ULOF, so unprotected loss of flow, where we have an instant reduction of pump head to 0. So that's, I think, beyond design basis, not design basis in that case. And what we did then was a sensitivity analysis of maximum temperature and power to flow ratios. And the results here are not all, you see how they, you change the fluid properties in that case. That's what we changed. And you see how these quantities then react to that. I don't really want to point too much to the exact results we got. I want to tell you why this is important. And this is really what we proposed is an augmented monitoring and inspection workflow, M&I. So that's originally suggested by Flanagan at Oak Ridge, I think. And the idea is you operate MSRs without conducting extensive irradiations in prototypical conditions to receive initial fuel qualification. Instead, what you do is you operate them and you monitor and inspect what your salt looks like at each point. So you measure its, let's say you measure its viscosity at a certain frequency. And then the question is, are you still in safe condition, or is that unsafe? And that's where our proposal comes. And the proposal really is use this code, use Griffin and Pronghorn to run these transients with the perturbed salt properties. Okay, these transients, I said, what are the transients? Well, you can have to come up with a set of transients. So ULOF would be one of them, but you have to come up with a set of transients that you think are relevant and cover the design basis sufficiently. So you run all of them. So you do a measurement, you figure out you want to figure out, is it still safe? So you run the end transients and you see if it's within bounds or not, and then you can decide if it's unsafe or safe. So that's a vision, and that's what we are working towards. Okay, let me see how I am on time. Okay. So my last topic here is nuclear thermal propulsion. So this is work that has started, well, about a year ago, with a new interest of NASA and the US in nuclear thermal propulsion systems. And what I've shown you here is basically a collection of different pictures from literature of how nuclear thermal propulsion systems looks like. If you look on the upper left-hand side, that's probably something you're familiar with. That's that is a NERVA type. So graphite hexagonal assemblies. B is basically a plain view of that. That is done in the 50s to 70s. If you go down, you see the GE 711 and ANL 200. These are fast reactors, CERMET type fast reactors. And then later experiments, the Russian experiments in E, a very, very weird geometry. You have this twisted ribbon, a very tiny twisted ribbon fuel element made out of carbide fuels, very resistant to temperatures, which is important, of course. And then finally, we go into the more recent designs, one out of Korea, that's F, and then G, a recent publication from the forgot about where that is, but that's the newest design that was published in literature just recently. So all of them have the same kind of idea. You just heat up hydrogen in a core, and then you put it out a nozzle, and that gives you, a very good speed, a very good use of your hydrogen on, let's say, your way to Mars, let's say. So where do we fit in here? We fit into that effort in two aspects. The first of them is the SIRIUS experiment series. So SIRIUS experiment series is a transient campaign. So you take the new fuel forms that are suggested by NASA, and these are in particular uranium nitride CERMET and uranium nitride SIRSA. If you're not familiar with it, CERMET and SIRSA are so ceramic metallic and ceramic ceramic. Ceramic metallic, the matrix is like tungsten, usually, let's say tungsten, and the fuel kernels is uranium nitride. That would be the ceramic. Ceramic ceramic is where the fuel kernel is, again, uranium nitride, but the matrix would be zirconium carbide, for example. That's would withstand higher temperatures. And these experiments are performed at TREAT. So TREAT is a transient reactor that is located out at the INL site. And it offers you unique capabilities to test your fuel in action in transient situations. Now, what are the challenges that you have with NTP fuels? So, the first one is it gets really, really hot. So it's 2600 to 2900 Kelvin that you have to withstand. The second one is fast heating rates, up to 100 Kelvin per second. And to test your fuel under these conditions, we put them into TREAT. We run a transient, or we run a prescribed transient on them. And then we take them out of the experiment, and we dissect the fuel at MFC, for example. There are currently four parts to that series series, and that is series 1 through 4, but most likely there will be more in the future. So series 1 and 2 have been done. So these experiments are done. The difference, and you see series 1 quite a bit, because that's really what I want to talk about in the results a little bit. That's a small specimen that is not cooled. So the specimen is in there in the reactor, and it's dry. And then you heat it up to, 2600 Kelvin, and that's been done multiple times. That's series 1. Series 2 is very similar to series 2 is similar to series 1, instead that the fuel is not INL fabricated, but NASA fabricated, so slightly different fuel. Series 3 moves on and makes this experiment a stack of those. You see the geometry, it'll be a stack of those instead of a single one. And then series 4, which is the first one that is actually of real interest because it's in prototypical conditions, because it has hydrogen with it. So there's hydrogen cooling, in situ cooling, while you run the experiment. So that's a very interesting design, and this is currently being designed. So series 3 design has wrapped up. Series 4 is currently being designed. When I talk about CAL experiments in the next couple of slides, what a CAL experiment is is really the calibration experiment. So in Treat, you run calibration experiments to figure out how much fuel, how much energy exactly is deposited in a fuel, in your fuel specimen without running the real experiment. So that's what the CAL experiment is for. And that's the focus of the next few slides. Okay, the CAL experiment. So this is a concept of the multiphysics simulations that we do for SIRIUS-CAL. So what that is SIRIUS-1-CAL. That's what I should say. So you have this fuel sample on the very right-hand side. That's the size of a quarter. So the diameter is the size of a quarter, a bit taller than a quarter, but it's quite small. So that sample goes into the sample holder that you see in the dashed box. And you put a lot of instrumentation in there. There's a pyrometer in there to measure the surface temperature. There are thermocouples in there. Then those go into the March system. So these are basically experiment holders. So you put one into the other, like a Russian doll kind of thing. And then finally they get into that March system, and that has a barrier around it. So when you release fission product, if you release fission products, you don't contaminate anything. So there are actually 2 barriers in total for every experiment. So, and that whole assembly then goes into the experiment cavity in Treat. So that's on the very left. So Treat, the core are these assemblies around it. And then the experiment is right in the middle, right here. That's where it goes into. And it's not big. It's about, let's say, 20 centimeters across this way, maybe. The S here, that stands for slotted. So these assemblies are all removed, so you can directly look at them. So you can have a detector here that looks directly into the core and sees what's going on. Okay, the rest then are fuel assemblies, and some of them are then transient rod assemblies, and others are safety rod assemblies, and so on. So you can see that the nomenclature down here. Okay, so you see this is a lot of scales that are going on here. So a few meters, about a meter, some centimeters in the middle, and then it goes down to like a centimeter on the right. So there's quite a number of scales in here. If you want to mesh everything at the scale of the smallest scale, it's going to be very expensive. So that's not what we do. Let's go in here. It's a more detailed look at what we do for multiphysics modeling. We currently do a 2-step process. The first step is cross-section generation, and we do cross-section generation with Serpent. So we run eigenvalue problems, so steady state problems with Serpent, and we get cross-sections. And the second is a transient simulation that we do with Griffin, diffusion with SPH equivalence. So we use an equivalence method. And we use SPH here. I mean, think discontinuity factor type, but SPH is slightly different, has a different spin to it. But it's in the similar vein of conserving relevant quantities over reference volume. So that's what we use. That's what we use SPH for. And we run that in transient. So the key here is cross sections generated in steady state, and then multiphysics is run in transient with these cross sections. During the transient, we couple Griffin neutronics and the thermal model. So there are 2 scales of the thermal model. The first scale is you need to keep track of the temperature of treat, because that will give you your feedback. And that's spectral shift in this case. So you have to know what the graphite temperature is at each point in time and space. So that's a, let's call it a global heat conduction problem that we solve. And that's what would be solved on the mesh that you see here. So that's a neutronics mesh. It is also the global heat conduction mesh that gives you the reactor feedback. We also solve for the temperature, explicit temperature distribution in the specimen itself. So this here is much smaller, the right-hand side, with the specimen that is included in there. But this is really what we're after. We want to see the temperature distribution, and we want to see potentially stress distribution as well, stress and strain. What makes this possible to have these two length scales and separate them? Well, again, the multi-up system, that's what we use for doing that. So let's talk about some results. So this is SIRIUS-CAL reactivity is a 55% delta K over K. So that's typical for a calibration experiment. The reactivity insertion is rather small. And the results we get, apart from the nice plots of thermal and fast, the thermal fluxes, is really what you really want to look at is the measured and simulated power trace. So this is the reactor power. And what you're looking at here is the Griffin curve is, so it's log. So the initial, that difference here is not so important. What is important is really what happens in the peak region. What you see here is Griffin. So the green line is Griffin. And then the other lines are detectors. So the RTC, ABC, those are detectors. And then the arc is the reactor control system, which has its own model. It's I think, not sure what they do, but it's their own model to approximate or to compute the reactor power. So you see, we have pretty good agreement here. One thing I want to point out, though, is that we have to do a little bit of work to achieve that. And that is we have to currently adjust the control rod slightly, the initial position of the control rod slightly, and then the control rod motion to get the initial period right. The reason is we are investigating that. It's a pretty interesting problem to investigate. Actually, it is somehow related to how much boron is in the core, how much boron is in the control rod. But this is for forthcoming work that will be very interesting, I think. Finally, we get the temperature distribution in the specimen. That's really what we're after. So the plot down here, that's the temperature distribution in the specimen. Now, it really doesn't get all that hot because it's a CAL experiment. So it gets only up to about 935 Kelvin. Yeah. Yes, so we would do the series 1, and then we know how hot it got, and then we have predictions for the PIE, what we think should have happened to this fuel. And that's really the goal of this exercise, and apart from, of course, validation. Let me go into some results about work we do with NASA. And this is what, again, is a reference plant design. And reference plant, want to stress that again, it's something that looks like, smells like the actual reactor, but it doesn't have the right numbers in it. You know, it doesn't have quite the right design in it. It doesn't have the right amount of control material in the drums and so on. So it is an open source design that can be shared more easily than the other designs. In this case, the core that is envisioned is depicted on the right-hand side. And this is a picture taken from a recent publication in Nuclear Technology. But this is how this core will look like. The difference to previous cores really is that if you look at this picture here, the pink is moderator, that's zirconium hydride, and it's a monolith. And the fuel is in these round assemblies in this cylindrical cluster arrangement. And the fuel is CERMIT in this case. So and is low enriched uranium. So there's a lot of stuff that has been changed from the previous 1970s designs. Okay, so what am I after here? I want to show you a transient. And I want to show you a transient where we rotate the drums from the initial position to introduce some reactivity and then see how the power changed, with the twist that we actually use a PID controller to do that. So the heating up of the core, bringing it to full power, is an important problem for NTP systems, because the longer that takes, the more hydrogen you waste on the way up. So you want to do that as quickly as possible. So that's why this is an important problem. Before I go into that, though, I want to talk a little bit about the control drum treatment in Griffin. And what we have there is quite a nice feature where we can actually we have a decusping method. that works for control drums. So you can rotate the drums, not in intervals, but to any position you actually want, and you get a nice, smooth and correct control rod, reactivity curve. If you see here on the right-hand side, this is rotated through 360 degrees for a microreactor. This is that example here as a microreactor, and you see that you get nice and smooth reactivity curves. Okay, let me talk about this NTP model a little bit more, because it's also a multiphysics model. This is a bit of a busy plot, but bear with me. So what do we do here? We use a multi-app system again. So in the multi-app system, we have one app that owns basically all the other apps. That's a primary app. In this case, it's Neutronics, okay? And the Neutronics app runs a full core heat conduction. So they have the same geometry, okay? So you solve heat conduction here on this problem, and then you communicate between them and you Picard iterate them. But then you also solve a conjugate heat transfer problem and a heat conduction problem for all of the assemblies, because they need to be meshed much finer to get the right level of details. We solve them separately. So these are all conjugate heat transfer and heat conduction problems that are then, the results are collected. They are imposed on this problem as boundary conditions. So on the global heat conduction problem, they are imposed as boundary conditions, and then you iterate between them. Okay, so that's a basic overview of that model. Let me see how much time I got left. Okay, the assumption here is, and that's not quite realistic, is we start with 100% hydrogen flow rate. You would probably have to ramp the flow rate up as the core heats up. Also, initial temperatures, 500 Kelvin is a bit too high. That was related to cross-section generation that we didn't want to rerun when we created those. It would start much colder than that usually. Initial control drum positions 120 degrees to 60 degrees, and then we control those using the PID controller. How do we do that? So we chose in this case to control the variable we control, or we want to, the set point variable is really reactivity here. It is not power. You can get reactivity from power by differentiation. If you can get a good idea what you need by differentiation in PKE equations. What we do here is then we feed this through a PID controller, and then we control the drum angle, okay, and then we get a reactivity back from Griffin, and we compute the reactivity using the IQS method. So we have an IQS. It comes for free basically in that case. For now, we do not limit the rotation to the speed of the drum. So you can rotate drums only a certain degree per second. That's ignored right now. So these are infinitely light, infinitely fast drums at this point. Now, this is pretty much the same thing, except there is a pre-treatment that I just mentioned. So power comes in, you pre-treat it, you get the reactivity, and then you do exactly what I said before, with one exception, the post-treatment here. The post-treatment just limits the axis motion, the control drum motion to within this interval, so 60 and 120 degrees. I will skip this slide here and go right into the results. So this is the first transient we ran, and we didn't tune the parameters that much. We basically stuck with the proportional constant of 25 and set the integral and the differential to 0. We set the, you see the set point for the reactivity is that orange line over here. Okay, that's how we want the reactivity to look like. And then the magenta or burgundy line is really the achieved reactivity. So you see, it doesn't match that well, and that's because this is not tuned very well. The other curves that are interesting here is, of course, the control drum angle. That's how you see how the control drum needs to move, or how the control drum is instructed to move to meet the set point. Yeah. Also, we have the power plotted in green. So that's a bit more on that. On the left-hand side, you see the average fuel temperature, average moderator temperature, and the average and the power. And what you can see is that the fuel temperature, of course, rises quite quickly and that's an average here. So the peak is a lot hotter, but it goes to about 2000 Kelvin in this case. The moderator temperature is only goes to about 300, 400. And that is because it is strictly insulated from where the heat is produced. And that's an important design feature, because that is not the moderator is not as heat resistant as the fuel is. So there are more results that I'm not showing here, where we actually started tuning the controllers, and you see that the actual reactivity starts following the set point reactivity a lot more. And this is done by not setting the integral and differential controllers to 0. I think this will be forthcoming in a publication sometime this year, whenever we find the time. But I have not included it in this presentation. So in summary, I want to impress on you that INL is the nation's premier nuclear science and technology laboratory. And in particular, my team, the Reactor Multiphysics team, we are at the forefront of solving some of the most challenging modeling and simulation problems for advanced reactors. And this work is relevant. It directly relates to the nation's energy future by ARDPs, private-public partnerships, and reactor demonstrations. I've shown you 3 examples. We work on a lot more stuff here. The 3 examples were pebble bed reactors, molten salt reactors, and the nuclear thermal propulsion systems. And I hope you enjoyed the talk, and I hope I have time for questions.
Yes, you do have time for questions, actually. There were about 5 minutes or so. So there were a couple of questions on the chat, but I'll see if somebody has a question in the room first. Okay.
Yeah, so questions of, can Griffin right now do burnout calculation?
Yeah, I heard the question. Yes, it can. Some of the development is some of the capabilities under development to make it nicer, but it can perform burnout calculations, yes.
For the molten salt fast reactors, there's a thermal hydraulics module that's calculated on the temperature profile. Does it include a thermal radiation component to it? If it does, what's the relevant impact of it?
It doesn't. Yeah, okay. So it's Pronghorn in that case. So it's multi-dimensional flow, and we use capability, if I may say, it's just straight out of Moose. So that capability exists in Moose. You can go to your computer and download it right now if you want. So this is not something that is export controlled, the TH side of it. The second part of the question is if we have radiation included, and the answer is we have not. So I can't answer that question. We have not looked into that.
Thank you.
There are 2 questions in the chat box. Actually, they're increasing as we speak. So Salim is asking, is there a full MTP system design developed? And if yes, is the design information available?
Okay, the answer is—
Roshan, your question's in chat.
What's that?
You can see it.
Yeah,
I can.
Okay.
I can actually. So yeah, so the answer to that question is it's under development, but the specific design information of the NASA design are not publicly available and won't be publicly available. However, there is work of several authors, if you're interested in designs that are open source, some from the 210s, from out of INL. And then there are some recently by Dan Kotlier from Georgia Tech. So those are publicly available. They look slightly different, but they are publicly available designs. Okay, the second question is there a reason for all the research now to be on thermal propulsion systems, but not electric propulsion? Okay, we don't make these decisions, which form you wanna finance or which one you wanna fund. The advantage of nuclear thermal propulsion systems is that they have a higher technology readiness because they have already been ground tests for NTP, and they typically have a higher thrust, if I'm not mistaken. So these are the two major reasons. Electric propulsion has other advantages. It solves the problem of what energy do you use for everything but propulsion on the system. It also has some advantages in mission planning. So when you go to Mars and you do your things, you have your reactor right there with you. And then you can use it, for example, to, I don't know, mine your fuel, your propellant. That's been one example that's been made. I'm not sure why electric propulsion isn't at the forefront right now, with the exception, really, it doesn't have as high a technology readiness. That would be my guess. Okay, there's an, sorry, go ahead.
I was telling you there is a third question.
Yeah, I have two questions regarding the treat work. First, I understand that you have to adjust the control rod so it would produce the same period as the experiment. As you said, the problem stems from the uncertainties in boron and hydrogen content. I was wondering if you added implosion traces. Poison, oh, yeah, okay. Poison traces like gadolinium and samarium to the core composition. Due to the operation of, okay, that's, I think, the first question. We have not. So the work there is, but similar. We will work with measured data on treat. And so we know the initial critical, the minimal critical core. We know that's supposed to be, critical. And we adjust the core boron to make it critical in our model. So that's a calibration of the model. And then we have measured treat data that we then match to that and see how well we do on critical configurations. And then that's the next step. We hope we match much better then. And once this is complete, we may look at adjusting the control rod worth. So because we have some uncertainty how much boron is in those, there's some modeling uncertainty. Some of it is largely homogenized, even in the Serpent model. And we would add an equivalent amount of boron in there too. So not gadolinium or samarium, but actually boron. So boron equivalent, basically. Do the operation of treat still requires a calculation of parameters like power coupling factor and transient correction factor? Correct. That's still how the treat operations do it. That's still how they do it. And the way that is done is that the power coupling factor is what is estimated in low power steady state. And then the transient correction factor is computed in a CAL experiment, for example. And then you measure the power trace of treat. And then you can compute from these two quantities, you can compute how much energy has been deposited in your sample.
Any other questions? Okay. Thank you very much, Sebastian. Let's thank Sebastian one more time. And thank you all for attending.
Thank you.